All right, what is the probability of rolling a 3 given that the roll is odd?
1 in 3.
Yeah, it's 1 in 3. How did you do that?
There's 3 odd numbers on a standard number cube.
Right. So that's the number of ways you can roll an odd number. Remember, given that narrows down our search. Normally there's 6 ways to roll a single die, a single standard random number cube. So that would be a 6 underneath, but we're given that the roll was odd, which means it can only be a 1, a 3, or a 5. There's only 3 ways to roll an odd number. How many ways can I roll a 3? There's only one way to get a 3. You get a 3. So the answer is 1 out of 3. Another type of problem, we've seen a few of these. A bag contains several poker chips or marbles or whatever it is. We have 8 blue poker chips, 6 are red, 5 are black. Calculate the probability in each scenario. Now, there's no green in the bag. So we're going to change green to red. What would the probability of pulling a green chip out of that bag be?
0.
0, because there's no green in the bag. We're going to change that to red so we actually have a problem to solve. Terrible. That wouldn't work either. The second chip pulled out is red, given that the first chip that you pulled out was blue and not replaced. So this not replaced thing, we have to visualize what that means. It means I didn't put it back, right? So now there is one less blue in the bag, but also there's one less chip in the bag, okay? So how many ways can I pull that second chip out of the bag? What's my denominator here? Yeah, because originally there were 8 plus 6 plus 5, 19 chips in the bag, but we already pulled one out, which means that there's only 18 chips left in the bag. Then we want it to be red. How many red chips are in the bag? There's 6. So 6 over 18, which is 1/3. So 1/3 of the time you'll pull out a red chip if you pulled out a blue chip first. Now for that second one, the second chip is red given that the first chip was black and replaced. What does that mean?
It's irrelevant.
It means I put it back, which means that this event, if this event was dependent, and it was, this event is independent because I put back that first chip, which means that has my probabilities changed at all? From the first pull to the second pull, do the probabilities change? No. So therefore, what is my probability? 6 red chips in the bag, 19 chips in the bag. There's your answer.
So if it says was replaced on the top, doesn't that just kind of make that part of...
That makes that first pull totally irrelevant. Yeah, it could have been anything. We put it back. It doesn't matter. And that last one, the third chip is black, given that the first 2 were red and not replaced. So now, what is my probability? There are 17 chips in the bag because I pulled 2 of them. And I didn't put them back. And now I want a red chip. Oh, sorry, I want a black chip. 5. There's 5 black chips in the bag, 17 chips in the bag total, so 5 over 17. So that's how you can work conditional probability in a situation like that. Just to take into account what has already happened, and then work from there. All right, the first part of this section was conditional probabilities using, what was that table called? Something table. Contingency table, good. We can also use tree diagrams. So this is like the second half of this section. We want to make a tree diagram to determine the conditional probability in this situation. What is the probability that a 6 will come up if you roll 3 dice? We don't know how to handle that mathematically yet. So we want to draw out this diagram. And on the quiz you guys took, I actually saw a couple of tree diagrams. I don't know if you knew that that's what they were. But some people actually did do a tree diagram on some of these, and it can come up with the correct answer for you. So we're going to roll 3 dice. How many ways can you roll 3 dice? If I can roll 2 dice by doing 6 times 6, then I can roll 3 dice by doing 6 times 6 times 6, which means that we have what? 216 ways to roll 3 dice. That's kind of an important thing. This is asking me for probability. So there's 216 ways for me to roll 3 dice. Now all I got to do is come up with the wins. How many different ways can I satisfy the requirements of this problem? To do that, we're going to draw a tree diagram. So kind of try to mimic what I'm doing here. 3 and 4, 5 and 6, 2 and 1. 1, 2, 3, 4, 5, 6, but I'm spreading them out. What this is right here is it's representing that first roll. I'm going to pretend, I'm going to roll all 3 dice at the same time, but I'm going to, in my mind, think of them as being one roll, and then another roll, and then another roll. So for my first roll, my first die that I'm looking at, it can come up as a 1, a 2, a 3, a 4, a 5, or a 6. Correct? Okay. Now my second roll, so this is the first roll. My second roll, let's say that first roll was a 1. My second roll then is going to be a 1, a 2, a 3, a 4, a 5, or a 6, right? Okay. So I can go and draw 6 lines. And that second row can be a 1, a 2, a 3, a 4, a 5, or a 6. Which means that over here, if that first roll was a 2, I can do a 1, a 2, a 3, a 4, a 5, and a 6 for my second roll. If that first roll was actually a 3, then my second roll can be a 1, a 2, a 3, a 4, a 5, or a 6, all the way across. Okay? Now if my second roll, let's say that second roll was a 1, so I have 1, 1, how many different ways can that third roll occur? 6 different ways. That third roll can be a 1, 2, 3, 4, 5, or 6. So 1, 2, 3, 4, 5, or 6. You will. You should like it. Now that means that this 2 here could be a 1, a 2, a 3, a 4, a 5, or a 6. The 3 could have a 1, a 2, a 3, a 4, a 5, or a 6 attached to it. And that's how this name tree diagram comes. Can you see how this is like a branch of a tree? Okay, now we don't have to draw in all of these things. That would take forever. The idea is to see the pattern that's forming. I want a 6. If a 6 comes up on my first die, or my second die, or my third die, I win automatically. I can get 2 6s. I can get all 3 6s. It doesn't matter as long as I see 1 6. Okay? So we're just going to follow this tree diagram down and count the number of wins that we get. If my first roll is a 1, and my second roll is a 1. Down this branch, how many wins do I have here? I have 1. My third roll would have to be a 6. Okay? So there's 1 win on that branch. If my first roll is a 1 and my second roll is a 2, how many wins would I have down that branch? 1. Because I would have to get a 6 on that third roll. If my roll was actually a 1, a 3, how many wins do I have down that branch? 1. Because again, I have to get a 6 on that third roll. What about 1, 4? I got to get a 6 for 1 total win. What about 1, 5? I got to get a 6 for me to have a win. What if I roll 1, 6? Because of that 6 right there, that's already a win, right? So does it matter what comes up on that third die? No. All 6 of these that would branch down from here are already wins because I've already gotten my 6, which means that all 6 are wins. How many wins do I have if my first roll is a 1? 6, 7, 8, 9, 10. There's 11 wins if my first roll is a 1. So logically then, how many wins will I have if my first roll is a 2? I heard somebody mumble 11. How many wins will I have if my first roll is a 3? 11. How come these are all the same? because the branches are all the same. Instead of a 1, I have a 2, but it's still going to be down here a 1, 2, 3, 4, 5, 6. And then each one of those is going to have a 1, 2, 3, 4, 5, 6 attached to them for my third roll, which means down this branch I'll have 1 win, 1 win, 1 win, 1 win, 1 win. But when my second roll is a 6, I have 6 wins for a total of 11. Same thing is going to happen here. What about if my first roll is a 4? 11. What if my first roll is a 5? 11. What if my first roll is a 6? What happened? Then everything's a win. And how many wins are there here? On each one of these branches, you have how many outcomes? There's 6 here, but there's 6 here for a total of how many outcomes? 36. Which means that there are 36 wins here. Each one of these ends of the branch is an outcome. I can roll a 1, 1, 1. I can roll a 1, 1, 2, a 1, 1, 3. Or I could roll a 1, 2, 5, or a 1, 2, 6, or a 1, 3, 4, or a 1, 3, 2. Each one of these outcomes that I'm not drawing because it would take forever. You have to use your imagination on this. You have to see that all 6 of these would have branches on them like this. And all 6 of these would have branches on them that look just like this. If you can do that, then you can visualize how each one of these things is an outcome. For the way that I can roll a dice, 3 dice, how many outcomes would I have all the way across if I went ahead and did that? If I wrote all of them out, how many would I see? I'd see 216 of them. We already know there's 216, so I don't got to do that. How many wins total do I have? 11, 11, 11, 11, 11. There's 5 11s sitting there. That's 55 plus 36 for a total of 91 wins. And there's only 216 ways to roll 3 dice. That is the probability right there. If the fraction reduces, reduce it. You want to write that as a decimal to get the probability. The answer would be 0.42. In other words, 42% of the time that you roll 3 dice, you should see a 6 on one of those 3 dice. So that's how you use a tree diagram. You don't typically draw the entire tree. You draw enough until you can see the pattern. Once you have the pattern, you can solve the problem very easily. All right, what is the probability of rolling all even numbers if you roll 3 dice? Well, what's the denominator going to be here? 216. We're rolling 3 dice. Okay. Now, I want to roll all even numbers. So I got to figure out how that can happen. How should I start, probably? Yeah, start making your tree. 1, 2, 3, 4, 5, 6. It is the same problem, but apply the problem to what we're doing to help you not have to do as much work. I want all even numbers. So I don't want a 1. How many wins do I have here? 0. How many wins do I have here? 0. How many wins do I have here? Why? Because those are odd numbers. I need all even numbers, which means as soon as I roll a 1, I lose. No matter what. Every single one of these outcomes loses. All of these are losers, all of these are losers. So I have to roll a 2 first. Once I roll that 2, that second roll can be a 1, 2, 3, 4, 5, or 6. But again, I want all even numbers. So if I roll a 1, that's a loser. There's no wins there. If I roll a 2, I'm good. If I roll a 3, there's no wins down that branch. If I roll a 4, I'm still good. Roll a 5, I'm automatically a loser. Roll a 6, I'm still good. So if I roll an even number on that second roll, now I can roll my third number. 1, 2, 3, 4, 5, 6. That should be enough to see the pattern. How many wins do I have if I roll a 1 for my first roll? 0. 0 for 3, 0 for 5. If I roll a 2 for my first roll, and then I roll a 1, I have 0 wins there. If I roll a 2, how many wins would I have if I rolled that third die? So there's actually 3 ways to win down that branch. If I roll a 3 here for my second roll, do I have any wins? No. How many wins do I have if I roll 2, 4? For my third roll, I'd have 3 wins. What if I roll 2, 5 something? No. What if I roll 2, 6 something? 3 wins. So if I roll a 2 first, how many wins do I have? There's 9 wins down this branch of the tree. So how many wins are there for 4? 9. How many wins are there for 6? 9. How many wins are there total? 27 out of 216, which as a probability, so the decimal version of that would be 0.125. 12.5% of the time you roll 3 dice, you should see all even numbers. That's 1/8 of the time. The key to this problem is the given that situation. We're given that we rolled all evens. So when I set up this tree, what am I going to do? I'm only going to use evens. So 2, 4, 6. Now I want to roll at least 1 6. Obviously everything over here is a win already. But we got to figure out all of these over here. So if I roll a 2 first, what can my second roll be? An even number. So a 2, a 4, or a 6. If I roll 2, 2, what can my third roll be? But I can roll a 2, a 4, or a 6. That's the critical thing. Yeah, to do wins, it has to be a 6 at that point, right? Because I got to go 2, 2, 6 in order to have a win. But this completes the branch. Completing the branch shows me how many different outcomes I have down this branch. So if there's 3 here, then how many outcomes do I have here? How many do I have here? For a total of 9. Which means I have how many outcomes total?
You can't count the ones that don't work, because you have to have a 6.
Yeah, but I'm doing wins over ways. What I'm doing right now is trying to find out the ways. How many ways can I roll 3 dice, given that I rolled all even numbers? This branch right here shows me there's 3 outcomes. There's 3 ways to roll 3 dice down this branch, which means there's another 3 here and another 3 here for a total of 9, which means there's 9 here and 9 here for a total of 27.
20 over 27.
So how many wins do we have down this completed branch right here? 1, 2, 2, 6. I want at least 1 6. So there's 1 win there, which means how many wins do I have down this branch? 1. How many wins do I have down this branch with that 6 sitting there already? 3. So I have a total of 5 wins here, right? How many wins will I have for 4 then? 5 as well, because I'll have 2, 4, 6, 2, 4, 6, 2, 4, 6, 2, 4, 6 for that branch for a total of 5 wins there. Now, how many wins do I have for 6? 9 total wins, because every single one of these is already a winner since I already rolled my 6. So this whole branch, this whole like side of the tree, all of those are winners. There are 9 outcomes here. 1, 2, 3, 4, 5, 6, 7, 8, 9. And every single one of them is a winner because of the fact that I already rolled a 6. I've already satisfied the problem. So how many wins do we have here total? We have 9, and 5 is 14, plus another 5 is 19 out of 27. The percentage there would be, or the decimal is 0.703, 70.3% of the time. What is the probability that one of the rolls was a 3, given that you rolled 3 dice and 2 of the rolls were odd? We don't know what the third roll was, but we know that the 2 of the 3 rolls were most definitely odd. So we want to set up a tree for this, but to do that you have to think about what that means in terms of the tree. So let's think about this. What do we think that might mean? You want to call the first two rolls odd? It would make your tree simpler. That's exactly right. Don't start with 1, 2, 3, 4, 5, 6. We don't know what that third roll was, so we have to count it as 1, 2, 3, 4, 5, 6. Count the odd ones first, because that's going to reduce the tree. So we got 1, 3, 5. How about my second roll? Count it as your second odd roll. 1, 3, 5. Now my third roll, what is that? All of them, because we don't know what that one was. 1, 2, 3, 4, 5, 6. So we're looking for probability, which means we're doing wins over ways. Let's figure out how many ways we can roll this situation. It's not 27. There's 3 ways to roll that first die. There's 3 ways to roll that second die. There's 6 ways to roll that third die, which gives me a total of 54 ways to roll those 3 dice. If you don't believe me, count them up. Down this branch, we have 6 outcomes. That means there's 6 outcomes down this branch and 6 outcomes down this branch for a total of 18 outcomes. We have 3 of those types of branches. 3 times 18 is 54. Okay, now, what is the probability that one of the rolls was a 3, given that you rolled 3 dice and 2 of the rolls were odd? We set up the tree with the given that thing. Now we got to worry about the number of wins that we have. So we want one of them to be a 3. Well, if I follow this branch, how many wins do I have? There's 1 here. That 3 right there is a win. If I follow this branch, how many wins do I have? All 6 of them are wins because I got that 3 on my second roll. So there's 6 wins on that middle branch, and how about this last branch? 1. Because down this branch, I gotta roll a 3. That's the only outcome that's a winner. All the other ones are losers, so there's only 1 winner down that branch. But down this one, there's 6 more branches here. All 6 of those are winners because of the fact that I hit my 3 on the second roll. And then here, there's still only 1 winner. I gotta get that 3 on the third roll. So there's a total of 8 wins down this branch of the tree. How many wins will we have on this 5? Also 8. Because the 1 and the 5 are exactly the same thing. What about down that 3? It is 18. That's correct. Why is it 18? There's 18 outcomes down each one of these branches, and because I hit that 3 on that first one, it doesn't matter what comes up in the next 2. I've automatically won. So there's 18 winners on that one, for a total of how many wins? We have 8, and 8 is 16, plus 18 is 34. 34 out of 54 as a probability would be point what? 629. 6? So that would round, if I was rounding to the nearest tenth, it would still round to 63%. So 0.6296 would be my good answer, and then if I'm doing a percent, I'd go 63.0%. So 63% of the time, if I'm rolling 3 dice, and 2 of those dice are odd, 63% of the time, I'll see a 3 on one of those 3 dice. All right. 4 coins are flipped. Find each probability. So, those of you who did the homework that I asked you to do, you have data. Those of you who did not, do not. And you will not understand what it is that we're doing, as well as the people who did. 4 coins are flipped. Find each probability. I'm going to ignore the probabilities here for a minute, and I'm going to create a tree diagram for flipping 4 coins. It's easy to create a tree diagram for flipping 4 coins because there's only 2 ways that a coin can be flipped. Either heads or tails, right? That would be a reflip. So, I'm going to flip my first coin. I had you guys flip quarters, nickels, dimes, and pennies so that you could tell the difference between the coins. In this case, each one of these parts of the tree, each branch of the tree is going to represent one of my flips. So for my first coin that I flip, it can either come up as heads or tails. Agreed? For my second coin that I flip, assuming that my first coin flipped as a head, it can come up as a head or a tail. For my second coin that I flip, assuming I first flipped a tail, it can come up as a head or a tail. For my third coin that I flipped, if I first flipped head, my next flip can come up a head or a tail. And I'm going to have a head or a tail here. And a head or a tail here. And a head or a tail here. This is my first flip. This is my second flip. This is my third flip. I have one more coin to flip. I can wind up with a head or a tail on each one of these. Four coin flips. Each one of them can only come up heads or tails. My first coin, I can flip all four of them at the same time. Because they're independent events, I can treat them as individually flipping each one at a time. I flip my first coin, I get either a head or a tail. Say I get a head. My second coin I flip, maybe that one comes up tails. My third coin that I flip, now I have heads, tails. My third coin, maybe that one comes up tails. Then I flip my fourth coin, so I have heads, tails, tails. Maybe the fourth coin also comes up tails. So I wind up with heads, tails, tails, tails. That's what this tree diagram represents. How many different ways can I flip four coins? 16. And that's it. I can flip heads, 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 tails. Heads, heads, tails, heads. Heads, heads, tails, tails. Heads, tails, heads, heads. Heads, tails, heads, tails, and so on, all the way through. Okay? The tree diagram shows you every possible way that you can satisfy flipping four coins. There are only 16 ways to flip four coins. How do I know it's 16? Because there's 16 outcomes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So, find the probability that at least one of the four coins that you flip is tails. At least one. Can I have more than one? Can I have 0? Can I have exactly 1? Yes, because it says at least one. So, how many ways can I flip four coins? 16. How many of these outcomes include at least one outcome that is a tail? All but one. There's only one way to flip four coins and have none of them come up tails, if all four are heads. So 15 of these outcomes out of 16 satisfy that requirement. What about 2 are heads given that at least 1 is tails? 2 are heads given that at least 1 is tails. How many ways can I flip four coins so that I have at least 1 is tails given to me? No, given that at least 1 is tails. What was that? Over 15. Why is this one over 15? Yeah, I'm given that at least one of them came up tails, which excludes the tree branch that has all heads on it, which means I've eliminated one outcome out of the 16, which leaves me with 15 possible ways for me to flip those four coins. Now I need 2 that are heads. The best way to do this is just to run through the tree and count up all the tree branches that have 2 heads. So, heads, heads. I already have my 2 heads. Now I got to go tails, tails. And that takes care of that whole branch. That's 1. I got heads, tails. I got 1 head here. Heads, tails gives me another outcome. Heads, tails. If I go to tails next, I have to wind up with heads. That's another outcome. This branch is dead. Tails, heads. I can go heads, tails. That gives me another one. If I go tails, heads, I can go tails, heads. That gives me another one. If I go tails, tails right off the bat, what do I have to have? Heads, heads, which gives me one more, and that branch is dead. How many did I wind up with? 6 out of 15, which would reduce to 2/5. Actually, I'm sorry. I did that one wrong. There's more. It says at least one is tails. I can have 3 heads, so I need to change this. This isn't 6, and it's not 2/5. So let's go back through this. At least one is tails. We can have 2 tails, but we can also have only 1 tail. So heads, 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 tails works. That's 1. Heads, heads. But I can go tails, heads. No, that doesn't work. I have to have...
You have to have 2 heads and at least 1 tail. So that one's...
So the trick here is the way that this is worded. I have to have 2 heads. I'm told that at least one is tails, but it doesn't tell me that the other is tails. It just tells me that one of them is tails, and I want 2 heads. So this 4th coin can be heads or it can be tails. We haven't talked about all 4 coins here. So that's why this problem actually needs to be changed. It is still out of 15, but we can have 3 heads. We can also just have 2 heads. We have to have 2 heads. We cannot have all 4 heads, though. So heads, 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 tails works. That's 1. Heads, heads, tails, heads works. That's 2. Heads, heads, tails, tails works. That's 3. Heads, tails, heads, heads works. That's 4. Heads, tails works. That's 5. Heads, tails, tails, heads works. That's 6. Now tails, heads, heads, heads works. That's 7. Tails, heads, heads, tails. Does that work? Yeah. Okay, that's 8. Tails, heads, tails, heads. Okay, that's 9. What about tails, heads, tails, tails? No. How about, so that takes care of that whole branch. Now tails, tails. Heads, heads works. And that's it. So it's actually 10 out of 15, which reduces down to 2/3. That's the correct answer. The wording on that problem can be confusing. It tripped me up. I totally forgot about that. At least one is tails does not tell me that the other one has to be tails. So it can be heads also. All right, 3 are tails given that 1 is heads. No, it's not the same thing. I'm supposed to have 3 tails, and I'm told that 1 is heads.
So it's 15 again.
1 is heads for sure, which means all 4 can't be tails, so it's out of 15. Good. Now I got to come up with the number of branches that give me 3 tails. So up here, only 1 works with this one, because as soon as I have that head, I have to have 3 tails. So that takes care of that whole branch. There's only one way there. But down here, tails, if I go to heads, I have to have tails, tails. So that's 2, and that takes care of this whole branch. So now I can go tails, tails. I can go to heads, but then I got to go to tails. That's 3. I have tails, tails. I can go to tails, but then I must go to heads because I'm told that 1 is a head. So for a total of 4. 4 out of 15. And the last one, none are heads given that 1 is tails. I'm given that 1 is tails, which means this entire branch right here is eliminated. So that's 1 outcome gone, so I'm out of 15. You like my hair? Then what? None are heads. 1 out of 15. That's it. We have plenty of time to do this problem. According to the meteorologist, there's a 20% chance of snow for the next 5 days. Sounds awesome. What is the probability that it will snow on each of the next 5 days? So if you ever look at a weather report, it'll say, you'll see 20% chance of snow 5 days in a row. And you're like, wow, it's going to snow the next 5 days. Is that true? No, it's only a 20% chance each day. But what is the probability that you would actually see snow on all 5 of those days? What do we do? This is a fundamental counting principle problem. What is the probability that it will snow on the first day? 20%. As a decimal, that is 0.2. What is the probability that it will snow on the second day? 0.2. And the third day? And the fourth day? And the fifth day? That is the probability that it will snow on all 5 days. When you multiply that out, what do you get? 0.2 to the 5th power, basically. So as a percent, that would be 0.032% chance that it will snow on all 5 days. And that is why being a meteorologist is a great job. Because you can predict that it's going to snow, a 20% chance of snow over the next 5 days. What are the chances that you're right, that it snows on one of those 5 days? Probably pretty good, especially if you live somewhere where it snows frequently, right? But what are the chances that it snows on all 5 of those days? Not even close to 1/10% of a chance. So on all those other days where it's sunny, and you're like, man, it was predicted to snow today. The meteorologist is terrible. Actually, he's not. He's just using probability to his advantage and saying, you know what, it's going to snow on one of these next 5 days. You got a 20% chance each day, which makes him correct when it doesn't snow, because this number is so small, he is correct. But when it does snow, it's not surprising because he said that it's going to snow, a 20% chance. So meteorology is a great job. You can be basically wrong and still be right.